Good morning, everybody. Just want to give everybody a 1-minute warning. We'll be starting in Good morning, everybody. It is 9 o'clock. Welcome to day 1 of PyData Seattle 23. Are we all feeling energized and ready for the next few days? Oh, okay, good. So I'm just going to introduce our speakers, and then I will turn it over, and it should be a wonderful session. Also, at the end, I'm going to ask that we clap louder so that there's a competition between the two rooms across from each other. Okay? So let's show some love. But today we are here for the next 1 hour and 30 minutes to learn about automated machine learning and tuning with FLAML. Did I say it right? Okay, I knew there was a chance. All right, and our speakers are Andreas Muller. He's a Principal Research SDE at Microsoft, and also OAC, you can see her as well. Nisha Desai, who is a Product Manager for Azure Synapse Analytics with Microsoft as well. All right, I'll turn it over. Before I do, of course, you all know there is food available, and then I hope some of you have found the restrooms. They're also around. And also, for questions, they have decided that they'll take questions as they come up. So we'll go from there. I will turn it over to them, but let's start with a warm welcome for them.
So hi, everyone. Thanks for joining our session. We're excited to talk to you about FLAML. So FLAML is an AutoML and tuning library that recently came out of our MSR research team, and it's since been open sourced and has gained a lot of traction. So we'll cover a few different topics today. So we'll start with a brief overview of AutoML and tuning, for those of you that might not be familiar, and just really set some context behind what this framework is trying to address. And then we'll kind of go into an overview of FLAML, some of the experiences, some of the APIs that are available through that. And then we'll do a deep dive into one of my personal favorite topics of how you can parallelize some of your tuning and AutoML experiences in FLAML. And then, I guess probably some of the more also exciting stuff is we'll go through some of the newer features that are coming up in FLAML as well. So, we'll start with an overview. And so, again, so the session isn't going to be super, there's no like hands-on activity, right? But you can go ahead and you can download any of these notebooks that we'll present or learn more about it through the GitHub repo. We have the link here. If you have any questions, like we mentioned earlier, just feel free to raise your hand and we'll get your question. So let's provide some context about like who is FLAML really for. So when it comes to FLAML, we know that from surveys that have been sent out, from even research that we've done on the product team for Azure Synapse Analytics, AutoML and hyperparameter tuning are things that are relevant for both data scientists and software engineers. But we're also seeing a lot of traction among these kinds of APIs, these kinds of frameworks for low-code, no-code users who really may not have a lot of familiarity with AutoML, with hyperparameter tuning, with they might just be getting started into kind of their machine learning experiences, but this provides them an easy way to be able to understand, how they can explore different hyperparameters and how they can kind of analyze some of their results. And so when we think about what FLAML is targeting, it's really all of these different kinds of users and giving them an easy way to kind of get started with machine learning or even do some more advanced explorations of their models. And so a lot of you might be familiar with this, so we won't spend too much time here, but the machine learning workflow has a lot of steps, right? Everything from getting your data to preparing it, to figuring out, okay, well, what kind of models do I want to use? How am I going to train my model to do specific machine learning tasks that I need it to do? Then we know that these models then get deployed, and that also has its own set of restrictions, constraints, challenges. But we know that in this development process, that there's a lot of iteration that happens, and there's a lot of trial testing that goes into improving this process. And so, for the general developer, finding a machine learning model requires a lot of decisions. This is everything from models you want to use, hyperparameters you want to try, and even when we take a look at the models that you want to use, you have so many different frameworks. And then even when you've chosen the framework, you then got to figure out how you implement it, how you train your data to perform for your desired task. And even along with this, there are a lot of choices to make. But even within that, we know that, like let's say you're starting with a light GBM model. There's a lot of different knobs and whistles that you have to also figure out what's going to yield the best model for you. You can experiment with things like the number of estimators, the number of leaves, your learning rate. But all of these things, depending on how you tweaked it, have a big impact on the results of your model. And so making the wrong selections can really detract from your overall model results and render your model potentially ineffective. And so the real challenge that we see, and the real challenge that we want FLAML to address is how do we help users find these ideal possible combinations, whether they know what frameworks they want to start with or whether they don't. But given a data set, how can we help users get to a highly accurate model as quickly as we can? And so this is where FLAML comes in. And so FLAML has been designed to really help users navigate all of these complex decisions. And so through the rest of this presentation, what you'll see is different ways of how FLAML is helping users make these kinds of decisions or explore these kinds of questions. We've seen FLAML be used across a lot of different industries and a lot of different scenarios. We've listed a few here, and so as we go through some of the demos later today, you'll see how FLAML can be used in some of these different applications as well. So then I'll pass it over to Andreas to go into a deeper introduction of FLAML.
All right, so this is FLAML is based on the research of Jiang at MSR, and unfortunately he couldn't make it, so I'm here to fill in for him and hopefully do his amazing work justice. So, so FLAML is sort of both. It's this research project that where they come up with new improvements to hyperparameter tuning in AutoML. There's also an open source project that's gotten a lot of traction and contributions from the community. So there's two main components that you can use. One is the task-oriented AutoML. So this is really machine learning specific high-level interface. It's a scikit-learn-like estimator, and you can say what kind of task you want to do, like classification or regression, and it will just do it for you. And the other one is to tune a user-defined function. This is standard sort of global optimization interface. You can do any kind of optimization that you want. You can write down a function with any like parameters or hyperparameters, and this could be an ML function, but it could also be anything else. And so the idea behind it is that FLAML is particularly tuned to do optimization fast, and it's very customizable. So you have these two different layers, the more sort of out-of-the-box AutoML and the user-defined function, but both of them can be highly customized, and so you can just sort of use the AutoML model as it is, or you can change what kind of models you want to do, what the time budget is, and there's a lot of ways to extend the API. And so here's sort of the two main things. As I said, the AutoML looks like a scikit-learn-like estimator. You have a class, and you can put in your configuration, and you can call fit and predict, and it just does the automatic machine learning behind the scenes. You can parallelize this, and there's actually like different modes. You can either give it a budget, in which case it will do some Bayesian optimization model search, or you cannot give it a budget, and that it will not perform search and will just do a zero shot based on some meta learning. And we'll go into this into more detail soon. And the other one is tuning a user-defined function. In that case, you give it a function here. The name of the function is just the train LGBM. You give it a metric that says how do you want to optimize it. In this case here, it's mean squared error. And then you give it the search space. So the main input for the AutoML is the task and then the data. For user-defined function, you can give it any function and a search space. And both of them then take the optimization hyperparameters like their time budget and so on. And so depending on like how much control you want to have, you can do either a sort of very automated thing or a very manual thing. So let's dive a little bit deeper into the task-oriented AutoML. So here, the idea is that given a machine learning task and a resource constraint, you want to find a model that performs very well in that task. So here, your input is really, as I said, the training data and the task type. And then you just call sort of fit on the AutoML class, and then you get a model that you can deploy. And so this is sort of the standard workflow you would do with any machine learning models. Instead of using your like grid search or whatever in scikit-learn, you would just use AutoML. It will tune it automatically. And it will search over the different models for you. So it has a built-in portfolio of like light GBM and scikit-learn-based models and some deep learning models, and it will search for them over them automatically. The tasks that are supported, so are the standard ones, which are like classification and regression, but then also there's time series tasks, which are quite common. So there's time series forecast, which is standard forecasting regression task. There's time series forecast classification, which is a forecasting class label. So it's a time series based classification task. These are very common, but they're not part of like most standard AutoML libraries. There's learning to rank, and then there's several NLP tasks. There's actually, and we'll come to this in the end, there's also specific tasks for working with large language models and dialogue-based systems. And so for classification and regression, as I said, it uses like standard gradient boosting models like CatBoost, like GBM, XGBoost. It uses scikit-learn. If you're running on Spark, it also uses Apache SparkML. And there's an open source library that comes from Microsoft called SynapseML that also can run both on Spark or locally. That also has some efficient implementations of gradient boosting and some other algorithms. So these are used for tabular data, so it's classification, regression, focus on tabular data. Then for time series forecasting, you again have the gradient boosting models, but also profit, PyData forecasting, and stats models, which have more like time series focused method. And then for NLP, it uses Hugging Face transformers. And so for each of them, it has built-in a set of models that will search over and build a set of configurations, and you just have to specify the task, and it will do the search automatically. You can either use this directly, or you can customize this for your use case. So there was someone that wanted to work on a security domain, and they had a specific classifier, and they had specific hyperparameters and performance criteria. And we'll show in the demo how you can customize the AutoML interface by providing a custom model. And then still all the other things will be in place for you, like how the data is split, and how the search is performed, and but you only have to provide the model and the configurations. So here's the standard sort of AutoML loop that is run. So as I said, importantly, you have the resource budget that's specified and the task. And then in gray, you can see the machine learning component, which is like you fit the model and then you predict on the model. In blue, you have the AutoML part, which is selecting the right estimator, so doing gradient boosting or random forest or linear models or something. And then for each of them, there's a built-in hyperparameter space. So configurations are sampled from the estimators and the hyperparameters. The model is trained on them, and then the loss function determines what estimators and configurations you select next. And so you can replace any part of this. You can use a custom loss, you can use custom estimators, and you can use custom hyperparameter search spaces. Or you can just use all the built-in ones. And then you can also customize how the ML procedure is done and how the final model are evaluated. Like, do you want to ensemble the models that you get out, or do you just want to use the best model? And yeah, so I'll walk through this now in a little bit more detail on the example of the flight delay dataset. So what we'll do is we load the dataset containing the flight delay information. So it's like airline flight, day of week, and whether it's delayed or not. We do this. We load the data into pandas. We want to predict whether the binary label, and so we'll use the built-in AutoML class, and first try to do this with the default model and just see how the results are. And then we can compare this to using a customized model. Oh, we have the demo. That's it, right? Okay, so because we have some demos that are also using Spark, we used the Microsoft hosted Spark offering, Azure Synapse Analytics, for which is a PM. You can run all this locally. Obviously, later on, if we have the Spark examples, you need to run up start up a Spark cluster. But yeah, I'm running this in Synapse, but you can all run this in your local Jupyter lab. So we start by loading the data set from AutoML, which is an online repository of data sets. We are split it into training and test set. So here you can see the data set. So there's an airline, the flight number, airport from and to, day of the week, time of day, and the length of the flight. And as I said, so using defaults is very simple. You can just instantiate the AutoML classifier like you would do a scikit-learn classifier, and by default it will search like GBM, XGBoost, CatBoost, random forest, extra trees, and linear regression with an L1 penalty. So here's configuration. So the things that we need to provide if we want to do search is a time budget and the metric, and then obviously the task. The task and the time budget are sort of the main input, and then I'm not going to run this live because we're giving it, well, just 2 minutes, but still. We call fit, and then it will run its the optimization procedure, and so you can see how the best error slowly decreases over time. And in the end, it finds the best estimator is like GBM with 302 estimators, 466 leads, and so on. So it found a model for you with hyperparameter settings. The best accuracy in the validation set is 0.675, and the training duration is 5.7 seconds. And if you want, you can get the estimator out if you want to inspect it, like look at feature importances and things like that. And then we can dump the whole AutoML, or we just dump the estimator, and then we can load it up later and use it for prediction in production. We'll now just evaluate it on a test set after we selected the model. And so here we have an accuracy of 0.67, area under ROC curve of 0.72, and a log loss of 60. There's also a loss file that we specified earlier that gives you a lot of detail about what are all the different hyperparameter settings that were tried, and what are the results, what are the run times, and so on. You can look at. And here is the accuracy over time, and obviously it goes up because, or this is the best result so far. Yeah.
Can we find this demo notebook in the GitHub as well?
It should
Yes.
be there. If you don't see it, let me know, and we'll make sure to just get them out right after this.
Okay.
But yes, it should be. It should be slightly late demo, AutoML. Yeah. But this is basically just a very simple, like, this was just calling AutoML.fit. So now I want to compare this quickly to what if we don't tune, and so we can just take a LightGBM classifier or an XGBoost classifier and fit the model, and you can see that they're actually already quite good. If you look at accuracy, if you look at other metrics might be slightly different, but you see that the FLAML with 10 minutes gives you a slightly better accuracy on the test set than either XGBoost or LightGBM, which are each like about 66 or 66.7% accurate, and FLAML is 67.3% accurate. So as I said, every part can be customized. So there's a model called the regularized greedy forest, RGF, which is not currently built in. So let's say you have your own favorite model, if you want to use it, and it has its own hyperparameters. You can write a class for FLAML based on the sklearn estimator, and you just have to take in what is the task, and then define the search space. So search space is a dictionary of name, where names are the hyperparameter settings, and the values are dictionaries that specify distributions for the hyperparameters, like random ins, log random ins, log uniform, and so on. So these are defined the search spaces for the candidates. And once you did that, then you can just run the AutoML model with this. So you can here instantiate AutoML, you can say add learner, give it a name, and give it a class. In the settings, I now specify as the estimators this RGF that I added to as LightGBM and random forest and XGBoost, and I run the search again. And now this is included, also including the search space that I specified. So obviously, if you add your own learner, you have to add your own hyperparameter space. For all the built-in learners, there's built-in hyperparameter spaces. Similarly, you can write a custom metric if you want, and just specify it in the setting as a custom metric. Right. So this is sort of the basic setup, using just the AutoML class with different customizations. Here's some result present. Shouldn't be FLAML. No. Okay. Here's some comparison against other AutoML libraries that are out there. AutoSKlearn, HyperParameter, H2O, Teapot. I think this slide doesn't include a comparison against the one that's in the other room right now, which is AutoGluon. But if you look at the newer papers, there's also comparisons against this. And so here, comparisons always with the same time budget, let's say of 60 seconds, 600 seconds, or 3,600 seconds. What are the results of, these are all relative results against FLAML. So if the numbers are positive, it means FLAML performs better given the time. And this is all on the AutoML benchmark. So this is a standardized benchmark framework. And so, yeah, compared with the other methods, really one of the strong emphasis of FLAML is to give you good results very quickly. And so if you look at these time constraints, FLAML is able to like find better results fast. And as you saw, it's very easy to use, so it really minimizes the effort, because you can just say, this is my task and here's the data. It also does some pre-processing of the data for you. I didn't really show much about this, but it pre-processes according to the learner. And so I just mentioned it. This is using the there's two versions of this. There's a parallel version and a distributed version. Parallel distributed version, and there's the single process version. The single process version uses the cost-frugal hyperparameter optimization, also known as the flow2 algorithm, and that's what's used by default and powers the search. So the other interface is for user-defined functions. So this is the tune interface. If you compare that to the AutoML, so AutoML provides you more structured tune. Basically, if you want to use it for ML, you have to implement more things yourself, but it's more generic, so you can use it to do really anything you like. And so you give it a resource budget, search space, and a user-defined function, and the output is the best configuration. And so user-defined function could be model training, or could be something else. So other applications are like algorithm configuration, optimizing mathematical models, or like doing LLops pipelines. One thing that I've been working on, or other people in my team have been working on, is database configurations, like how do you want to configure your Spark clusters to run very fast on your workloads. So you can use it for this. So just optimize any function, basically. Do we have time for the set? Do we want to do the demo? Okay. Cool. So, and so I want to show then how we can use Tune with, again, a machine learning task. So that you can use other tasks, but machine learning is probably the one that we're all sort of familiar with. Okay, so back to doing machine learning with the Tune interface. So now, wait, this is Spark. Yeah. Yeah. So what we're doing here is we're actually, we're using, we're loading the data onto Spark, and then our user-defined function will be doing machine learning on Spark, and we're trying to optimize the hyperparameters of the machine learning model. So first, we load the data set, we created a Spark data frame, we use a vector assembler to prepare it for doing machine learning in Spark. We split it into train and test data. We use the SynapseML, which is a Microsoft open source library for the LargeDBM regressor. And we define our user-defined function here, which is a train, which creates the LargeDBM regressor, fits, and outputs the model and the evaluation metric. So we can just run train once with some parameter setting and get an R-square. So this is house price prediction, so it's a regression task. And so here, this is the result using a given set of parameters just during train once. And so train gives us back a score, and now we can use tune to tune the hyperparameters to optimize this metric. For that, we have to define the hyperparameter space. So now, because we're basically doing everything manually, we have to say, okay, here's alpha, the regularization parameter for LargeDBM, the loading rate, number of leaves, number of iterations, and we specify the search space using these built-in distributions for FLAML. So here we say alpha is uniform between 0 and 1, the learning rate is uniform between 0.001 and 1, and number of leaves is random and number of iterations is random. So here, these are not actually, like we don't sample here, we just specify the space. And so these give back objects that are specifying the search space, which will later be searched, used in search. And we define FLAML tune, which is the function we actually want to tune, which takes into config, hits it to train, and then we just return the metric. And then we can call tune.run. We give it the function and the parameters and the time budget. And then it will start the tuning process. And so if you use tune, it will actually use an algorithm called blend search, which uses a blending of Bayesian optimization together with the cost-frugal search that we saw before. And then you see it will like run all the trials for you, and then in the end reports time and R square. And then in the end, you can get the best config, and the best config is this alpha learning rate, number of leaves, number of iterations. And now we can use that configuration in the train function to see what are the actual results. So on the test data set with the original model and with the tuned model. And you can see that if we tune this light GVM version, then we go from R square of 0.7 to an R square of 0.8. So that's quite a big improvement on this regression data set. So here, yeah?
At the very beginning, for some reason, you were doing repetition to 1.
Sorry?
At the very beginning, on the first cell, you're doing repetition to 1. And reason for this?
I do...
Like you log in initial data and then do repetition to 1.
Actually, I'm not sure why.
I mean, looks like it's just going to be running on one node, right?
Yes.
Okay. I mean,
I'm actually not sure if it's... Oh, I think it's distributing the tuning. So each... I think each model instance will run on a different node.
Okay.
I think that's the intent. But each node will have all the data because it's a small data set. Okay, yeah. So again, this is in this case doing AutoML, but doing it sort of the more manual way by controlling everything ourselves and writing our own learning function. And so we could use the same thing to tune any software system or optimize. This is often also used if you have if you want to optimize a process that's outside of your direct control. Like if you want to optimize something that involves like a real-world process. Say this is used for like in material science or in pharmacology, where you have to run an extra experiment to see how well something is, and then you feedback the result. Yeah.
Can we try different metrics at the same time, like R square, MEC, MA?
Yes, there's actually going to be a side. So usually in Bayesian optimization or hyperparameter tuning, you optimize for one metric. There's actually later on, when I talk about the more recent research, there's something that she worked on that optimizes multiple metrics at the same time. When in that case, you have to give like a priority, like which metric is most important to you. Yeah, and so, I mean, so Tune is basically, it's more flexible interface, and you can use it with any machine learning software or any other software or like processes in the real world. But still, you can do very tight budget constraints, and it will optimize within the budget constraint. So here, this is sort of an overview of the different methods that are actually under the hood. So the Flow2 and constructal optimization are the two main papers that the basic algorithm is based on. So these are local search results that are provably efficient. So compared with other Bayesian optimization methods or hyperparameter optimization methods, these provably give you fast results, but they only do local search. So this is used by default if you use the AutoML. And then there's OneSearch, which combines global Bayesian optimization with local search. And this is used if you use Tune or you use AutoML on multiple nodes. Then it spawns different worker nodes which each do local search, which are then later combined in global search. There's also online tuning and meta-learning, and then the meta-learning, if you don't give a budget to the AutoML, it will actually do zero shared learning. And finally, there's the eco-optigen, which is for tuning large language models, and I'll talk a little bit more about this later. So these are sort of all the different things that are available in FLAML, and they all built upon this Flow2 and CFO, and then there's several layers on top of the CFO that add like meta-learning, online tuning, and global search. Back to Jiang.
Well, thanks. Okay, so in this next section, what we'll do is we'll do a deep dive on some of the more advanced functionalities with FLAML, and how we can use some of these things to help better tune our applications. So we'll start by just providing a high-level overview of the different constraints that FLAML offers. And so there's three different kinds of constraints. You can set constraints on your overall time budget, so your wall clock time that you want to assign for your overall AutoML experiment. You can also set a budget on different constructor arguments, right? So if there's certain kinds of fields or certain kinds of models that you want to be able to tune. And the last is that there's model-specific constraints in terms of the amount of time, say, that you want to spend tuning a specific training job or the time for a model to run predictions. And so here we have an example of how you can use FLAML to do some more kind of advanced constraints and provide those configurations when in your tuning scripts. But let's say you have a AutoML task and you want to restrict the training time for each model to be 1 second. You want the model to have a prediction time of a fraction of a second, and then you also want to be able to combine both the training and validation loss, so create your own custom metric and make sure that that custom metric will be less than a particular value. So this is one example of how you can specify all of those different configurations in FLAML. In addition, FLAML also provides a warn start functionality. And so let's say you have had a training job that's been running for 2 hours and had a best set of hyperparameter configurations. A week later, you want to be able to pick it up and say, hey, I want to restart and kind of pick up in this AutoML or this tuning job, and I want to be able to run additional sets of configurations. You can use the warn start functionality to basically be able to just pick up from where you started, which is a pretty neat function if you're not doing everything in just one sitting. The last is around the parallel tuning, and so FLAML provides Spark as an option for parallelizing some of your AutoML experiences. And so there's kind of 2 different modes, and I think we talked about this a little bit earlier, but the first note is that you can do everything sequentially. So this is particularly helpful, let's say if you have large Spark-based models and you just want to be able to parallelize the tuning or the AutoML experience for those Spark-based models. That's one case where you might want to run things sequentially. Another example is that you can also parallelize the individual AutoML trials. And let's say the data set's small enough, your models are small enough, and you want to be able to run training across all of your Spark nodes or all of your Spark executors. You can do that just using Spark as well. So a few different ways in how you can kind of optimize your training time. If you're using Spark, you have a few different constraints or I guess configurations that you can tweak. And so similar to sklearn, you can specify the number of jobs. And so this will be how many cores you want to allocate to each training job. You can also say how many parallel trials you might want to run. And so by default, Spark will run one trial per executor. But you can also customize this as well. And so in this next example, what we'll see is how we can read a Spark data set, and we'll use Spark to kind of do all the ETL for it. And then we'll train a SynapseML like GBM model. So again, kind of similar to some of the tuning example that we saw. This is a Spark-based model that will then tune. And we'll see how, even on this tuning example, we can boost our accuracy or AUC score. And then we'll also do some other kind of comparisons where we can run FLAML AutoML on the Spark data set, and we'll use it to kind of do a search of Spark-based learners. And we can also use FLAML and Spark to parallelize these AutoML trials. So a lot of different combinations that we'll see. So let me just jump over. So yes, so as I mentioned in this example, what we'll see is how we can use SynapseML, FLAML, and Spark all together. And so I'll just go through. So here we're going to start by just loading our data. In this case, we're going to be working with a bankruptcy data set. And so this contains a bunch of information on the company's operating gross margin, profit rates, etc. We'll then generate our training and test sets with Spark. And then we'll use some of the Spark featureizers to basically transform our data set and generate our training data. Then we'll start with setting up our default SynapseML like GBM model. Again, this is like one of our Spark-based models, so we'll see how we can use that later on. And then we'll just define our, we'll use our default model and generate our kind of default metrics so we can kind of come up with our baseline. And so here we can see we have an AUC of about 0.66. And so the next piece is we'll run our FLAML tune. And so here we have specified our training function, and we'll specify all the different places that we want to search over. And so here we'll explore things around like our learning rates, number of leads, number of iterations, and we'll use AUC as kind of our metric that we want to optimize against. And so in this example, I've just provided some simple constraints, but basically what we'll be able to see as we run tuning, we'll get back our optimal model, and we'll see that our optimized AUC score is around like 0.81. But the thing that I wanted to highlight here is here we're able to take our Spark data set, feed that into our tuning. We're not restricted to work with the specific kind of data frame. We can also kind of support Spark in this example, and then also see how you can work with some of the Spark-based learners when doing tune. Next, in the AutoML kind of section, we'll see how we can then take Spark to be able to parallelize some of our AutoML trials. And so in this first example, what we have is we're just doing a simple classification task. And what we'll do is we'll actually convert our Spark data frame into a pandas on Spark data frame. So basically just another wrapper, kind of another interaction that you can have using your familiar pandas APIs just on top of Spark. But as you can see here, it's still a pandas PySpark data frame. And so then we can run AutoML and fit it just on top of that pandas PySpark data frame. And here what we'll see is that it'll go through a list of Spark-based learners. And so one of the things that on the projects that we're kind of helping contribute back to is adding a lot more, additional Spark-based learners to this list. But then we'll go through and kind of go through all of the different combinations for this AutoML trial, and we'll see that, we'll spit back our best optimized model, which has, our AUC or ROC score for 0.93. So again, we can see some pretty significant improvements on this data set when using Spark and the results that we see. So the last section of this, I want to show how we can use Spark to parallelize, just run multiple trials at the same time. And so in this example, like I mentioned, we'll set our number of concurrent trials to 2. And then we'll see that in this case, we'll go back and we'll convert this back into a pandas data frame so that we can run the training across all the nodes. And then here we'll just fit our pandas data frame on our AutoML experience. Ooh, looks like there's an error listing this is running. Yeah, so and then, so unfortunately, I guess the last 2 reads something changed, but once you switch this back, you'll be able to see that once you've kind of executed the AutoML trial, it'll go through and explore a lot of different kinds of learners. So this isn't just restricted to Spark when you're parallelizing, right? It can run all your scikit-learn-based learners, like GPM, other kinds of frameworks. And then it'll also come back with kind of your best model. Unfortunately, in this example, I think the notebook output got cleared for these last 2, but it's okay. But then we'll kind of skip back. So here you can see there's a lot of different ways that you can use Spark to kind of decide how you want to parallelize or improve some of your execution for your experiments. In some cases, when you're doing parallel versus sequential tuning, parallelizing it might not be your kind of best option. This is particularly, highlighted when you have a lot of, if the overhead and the trial time for running all of these things might not be worth it. And you might also want to consider things like how if you're using Spark, the randomness might get affected, or the availability of even some of your parallel resources and the cost of these. So these are all some factors that you might want to consider when deciding when you want to parallelize or run sequentially. We have an example here. We won't go through all the math, right? But you can kind of understand that depending on the overhead time of running multiple trials and the different nodes having to communicate and coordinate with each other, it might not always be the most efficient. And so there's some kind of like rough math that you can take a look at on how, when you might want to use some of these kinds of features. But I think in the next section, what we'll now cover is, the next section we'll then cover is I'll pass it back to Andreas, and we'll go through some of the newer features around OpenAI and these other configurations.
Thank you. Okay, so we had a question earlier about okay, how can I deal with multiple objectives? And so there's this recent work which is going to be published this year in iClear by Jiang and his collaborators on target hyperparameter optimization with lexicographic objectives. So here the idea is that you have multiple objectives together with a priority ordering. So the most standard is single objective hyperparameter optimization, which we saw before, where you basically want to optimize accuracy given a budget constraint. In multiple objectives, you usually have, you're looking for a Pareto frontier, but it's like usually hard to choose how you want to do that. But the setting that we're looking at here is that you have multiple objectives with a priority order of the objectives. So for example, the loss, the number of features, and how stable it is. So you can do this in FLAML by specifying the metrics. So this is the only thing that's really required, but then you can also specify tolerance and targets. Tolerances say within how much something should be basically considered as optimal, and the target should be the optimization value, like if you want something to be 0 or 1 or 5 or something like that. There's also a demo in the repo, but I think we're not going to go into this since we have some other demos. Actually, I mean, we have. But I think, yeah, what I want to go into in a little bit more detail is tuning large language models and for basically accurate and cheap inference. So here, cost-effective is quite literal in that most of these large language models are behind APIs, and you have to pay per call, per token. And so we've seen that like the way you phrase a prompt, which model you use, the temperature you use, the length you use, of tokens that you want to predict, and so on, has a pretty big impact on how accurate the results are. And so similar to standard machine learning, these you can consider like these, like the prompt structure, temperature, and so on, as like hyperparameters that you want to tune. But running these models is very expensive, and so ideally you want to tune these hyperparameters by doing a minimum number of queries to the model, and since they're also usually charged by token length, you want to use a minimum number of tokens. And so FLAML has this integration that allows you to tune by or while taking these constraints into account, and it's specifically optimized to work with a restricted number of, limiting the number of tokens and limiting the number of calls. Okay. So I'm going to show you a demo for that. Okay, so for this you have to pip install FLAML with the OpenAI integration. So you need obviously to run these models, you need an OpenAI account or an Azure OpenAI account, and so here we use the Azure OpenAI integration, and you need to get your API key, and then you can use these models. We're using the OpenAI human eval dataset here, which is a Python code generation task. This is a standard large language model benchmark task. The prompt here is the function name and a doc string, and we want to generate code for the function. The dataset contains 164 samples, and we use the first 20 for tuning the generation hyperparameters and the rest for evaluation. So one of the things that actually kind of allows us to tune here is that we have a way to measure whether generation is good or not. In this case, this is unit tests. So in this data set, we have unit tests that check whether the function does the right thing. In general prompting tasks, that's quite tricky. if you can do that, that makes tuning much easier. If you don't have an automated way to check how good a prompt is, it's going to be much harder to use this. Okay, so here we specify what we want to tune. So we load a data set. We say we want to tune on the first 20 points, and we're using the prompts from the data set. And so here, this is one of the prompts where you can see there's the definition of the function, def, compare, gain, guess, and then there's kind of not very succinct docstring that says you want to compare two lists basically and give the absolute value of the differences. And the task is for the large language model to write a Python code that implements the function. And then there's the test cases included that say basically whether the function was implemented correctly by the model. Obviously, like the first test, like the Python code needs to run, but also it needs to evaluate this way. So if you want to have the absolute differences between 0 and 0, it should output 0, and so on. So we define the success metric. Success metric is that we want to execute the code. So we do subparameter that says run. We get the code, we write it to a file, we run it, and unless we timeout, or in case there's an error, we return 0. Otherwise, we return 1 if it succeeded. And then we write our success metric as the number of successes. So here we can. So in many large language model tasks, you don't only want to provide a single answer, but you want to provide multiple answers as a recommendation to the users. If you have a co-pilot-like experience, you don't want to just give it one answer. You want to provide answers that are all plausible, and the user can pick from them. And so one of the success metrics that we found works very well is that you check not only, so the default that's used by the benchmark is you check if any of the answers or any of the top tier answers is good. So you check if any of them work. But we found for optimization it's better if you see how many of them are successful. So your return of the number of returned things, that it's a parameter how many results you want to return, how many of them were successful, and we try to tune that. Which is different from, as I said, the benchmark metric. So there's this, so completion tune is the interface for doing the tuning of any large language models. And so we just initialize it, and then we define the search space, and this is actually, so we pick different models, so there's TextAda, TextBabbage, TextDaVinci, 3.5 Turbo, this is ChatGPT, and GPT-4, which is the newest model. Then we say what parameters to tune, which is the temperature, which is a uniform between 0 and 1. And if you're not familiar with it, in these large language models, low temperature means deterministic results, high temperature means more probabilistic results that are sort of more creative or more like have more variance in them. And top key is a different way to basically specify something similar. And then we can specify what's the maximum number of tokens that we want to get returned. This is both a hyperparameter, but also influences strongly like how much it costs, because if you want to create more tokens, the call will be more expensive. And then n is the number of responses you want to get from the model. Again, this is a hyperparameter, but also changes how much it costs, because like basically n is a multiplier for the cost, because for each completion you want, you have to run a model, and that will cost you each individually. So what's different here from standard AutoML? Well, there's several things that are different. One is we have a separate inference and optimization budget. And so before we had an optimization budget, which basically said, okay, I want to tune this for 5 minutes, and then I want to get the best model. Here, we can say, okay, I want to tune this for $20, and then I want to get the best model. But also, there's an inference budget which says, I want a model that only costs that much. And so, for example, running GPT-4 is much more expensive than running GPT-3. So you could run GPT-3 like, I think, I forgot, maybe 100 times instead of running GPT-4 once. And so you specify not only how much money do you want to spend to tune the model, but also how much money do you want to spend on each call of the model during prediction time. And so you have two budgets here now that you specify. So here you can see the call to the tune. So you have the data, the metric. We want to maximize the expected success. And we have the inference budget, which is we want to pay 5 cents per inference, and we have the optimization budget, meaning we want to spend $3 optimizing to get the best results. We also specify different prompts, and so here the prompt variable, or the prompt template here, is what's part of the data set, so it's the function name plus the docstring, but then we also have different sort of prompt engineering techniques here, where we also put something else in front of the prompt, say Python 3, or complete the following Python function, or complete the following Python function while including necessary import statements inside the function. Okay, and then we can run it, and so it will respect your budget constraint, it will respect the constraint for the prediction time budget, but also it will search in a way that optimizes the number of calls. So you want to minimize the amount of money you spend during tuning, obviously. And so whenever something looks like it will be too expensive during prediction time, it stops early. So it just basically, it starts from the 20 examples that will be used for evaluation. It just first sends one and looks how expensive it's going to be to run the other ones. And if it looks like it's going to be too expensive, it will not run them, and it will pick a different configuration if it's cheaper. So it's very aggressive in pruning the search space to make sure that you don't spend too much money during tuning, and you get a cheap function or a cheap configuration out. So here you can see that after the optimization, the prompt is complete the following Python function. So that worked the best from all the prompt engineering. Let's use text DaVinci 2, and this number of maximum tokens, number of completions, and temperature. And then you can use this configuration to do the completions on the test data. And you can see the expected success rate is 37. The success, which is like a top case success, is 77. And the inference cost per sample is 4 cents, whereas and the total cost is about $7.70. Any questions on this example? I want to briefly, since we have quite a bit of time left, I want to briefly go over another demo of tuning a model. In this case, it's tuning basically ChatGPT to solve the math benchmark problems. And so this is another large language model benchmark, and the idea is to solve a math problem with chain of thought style reasoning. Again, you obviously need to have an OpenAI subscription and have your keys, and again, we're loading a data set. This is the Hugging Face data set module is just called data sets, which is great. We take out, there's different levels of algebra questions, and we take out level 2 questions, which are sort of a little bit easier. And so here, this is what they look like. The sum of Jim's weight and Bob's weight is 180 pounds. If you subtract Jim's weight from Bob's weight, you get half of Bob's weight. How many pounds does Bob weigh? Okay, so simple algebra question in text form, and then the solution looks something like this, which is like a mixture of text and LaTeX. So again, we need to define a success metric that we can do automatically, and so here, this is basically parsing the LaTeX to get the result. I'm not going to go through the details. And basically parses, so it parses the LaTeX to get out fractions and the numbers and all kinds of different things. And then in the end, it compares that against the desired answer. So this is kind of tricky because the output of the model is LaTeX, and the desired answer really that you want to check if the number is correct. And so, but there's many different ways you can represent the numbers in the LaTeX mass and so on. And so you can also check if the chain of thought is correct, but I think we're not doing this here because that would be even more complicated. Okay, so now we can again try to tune the model. We're selecting between two models because this is a more complicated task. We compare the ChatGPT, which is GPT 3.5 Turbo, and GPT-4, and we select the temperature and maximum tokens and the n, which is the number of completions. So again, here we specify the inference budget, which is 3 cents, the optimization budget, which is $1, And then you can see the different trials. And actually it errored. That's too bad. No, it didn't. And so you can see that in the end, okay, getting 50 prompts with 770 max tokens and using GPT-3.5 Turbo was best. So it was actually good to get to use the cheaper model and use more prompts than to use the more expensive model to solve these algebra problems. If you look at the paper, you can see that if you use higher level algebra problems like the level 4, I think, then you, maybe even for level 3, then using GPT-4 is better than using GPT 3.5 because for the more complex questions, you need a more complex model. And for the simple questions, basically calling the simple model more often is more cost effective. And yeah, here's some of the prompt results. And yeah. All right. I think this was all on tuning the models. So really the key takeaway here is that we can use similar techniques to AutoML, but really we can work within these two different constraints, the inference budget and the tuning budget, and the specific structure of the inference budget allows us to prune some candidates very, very quickly so we can focus on the models that are cheap enough to actually run in production. All right. So this sort of concludes all the demos and features we wanted to show. I want to talk a little bit about the ongoing development as well. So there's a huge number of contributors from both academia and industry. So this is not only like a Microsoft project, there's people from Databricks, from any scale, working on this, many universities. And so this is both like cutting edge research that's being published. As you saw, there's the lexicographic metrics, is something that's an oral and iClear this year, but also something that is integrated into many products at Microsoft and other places. And so this is a huge open source community as well, so if you want to contribute, you're welcome. There's a contribution guide online and a roadmap for upcoming features. Do you want to work on any of them? If you have a specific application in mind, and you need to add features for your applications, come to the issue tracker. If you just go try it out, if you find bugs, issues, let us know. You can also, if you don't want to go to the issue tracker or just talk to developers, there's a Discord, and so you can just share what are the things you're working on. In particular, interesting are like the new things like the multiple lexicographic metrics or the tuning large language models. But if you have any use cases for any of it, just come on the Discord and chat with us. Several things that are currently in development is like more generative tasks, improving autonomous AI along the lines of AutoGPT, and improving always the robustness of the library. Yeah, you can find more on documentation and GitHub. And so there's all of the demos we show should all be on the GitHub. If you can't find anything, just shoot us a message. And so this is like the current list of papers, but new methods are being constantly added. So if you want to know more, I think the original FLAML paper, and it's probably one of the most more interesting ones. And then for the more recent work, the cost-effective hyperparameter optimization for large language models shows how you can provably get results for that are cheap both in terms of inference time and in terms of tuning time. Sorry, not inference time, but inference time costs and tuning time costs. Yeah.
All right, everybody, let's give them a round of applause.